Okay, so here we have a cone-related rate problem. It says that a 10 centimeter tall funnel is being drained with water at a constant rate of 10 cubic centimeters per second. The mouth of the funnel is 12 centimeters in diameter. How fast is the solution level dropping? How fast is solution level dropping when there are 200 cubic centimeters left in the funnel? Keyword when. And here we have the formula for the volume of a cone. Okay, so let me label the constants on the picture that I already have here. Here it says that the funnel is 10 centimeters tall, so that's going to be constant. So I can label that on the cone already. This is going to be 10. And it says that the mouth of the funnel is 12 centimeters in diameter. That's also constant, so if the diameter is 12, then that means the radius is 6. And notice they're both centimeters. Okay. Now, it says that the funnel is being drained with water at a constant rate of 10 cubic centimeters per second. Okay, so this is talking about rate. So this is a keyword rate. Now you have to ask yourself, okay, this is the rate of what? Well, cubic centimeters, that's a measure of volume, right? So that means that this is the derivative of the volume with respect to time is equal to, since it's being drained, it's not 10, but negative 10 cubic centimeters per second. Okay. And then it says that the mouth of the funnel, so I already have that, but then okay, so here it's asking me for how fast is the solution level dropping. So this is the actual question. So how fast is the solution level? So it's asking me for the derivative, in this case, of the solution level. So I don't have a variable for that yet. So let's assign one. How about we call, let's draw the solution level on the cone here. Let's say that this is represents the solution level. And so let's call that h for height. So that means that what I'm looking for is the derivative of the height with respect to time, the height of the water. Okay, so now that I have that, well, let me write this down. So I'm looking for the derivative of the height with respect to time when there are 200 cubic centimeters left in the funnel. So that means that when the volume is equal to 200. Okay, so now that I have all of my information, let me just write down this guy. Let me just put it down here. So I'm going to put it dV over dt is equal to negative 10. Okay, so now I have my picture. V equals 1/3 pi r squared h. Okay, now here I have a little bit of a problem. You see, I know that the radius of the cone is 6, and I know the height of the water level. Well, I know it's represented by h, but I don't know what it is. And then this, notice that here I have another, this is like another little mini cone, and I have another little radius down here, but I don't know this either. So this is just a little trick that'll save you a lot of work, is that notice that here I have two different variables. So if I get the derivative of both sides how it stands, I'm going to have to use the product rule, because both the radius and the height are functions of time, not of the cone, but of the water level. So here, if you take a look at this, you notice that inside of here you have two triangles. You have this big triangle and then you have a little triangle. And you notice that these are actually what we call similar triangles. And so since these are similar triangles, well, that means you can use this information to write the radius in terms of the height or the height in terms of the radius. Okay, so since I can do that, well, let's set up a proportion. So this means using the similar triangles, that means we can say that R over H is equal to 6 over 10. Okay, so if I want to write the radius in terms of the height, I would get that R is equal to 6/10 H, which is the same thing as 3/5 H. And then what I can do is I can grab this guy and plug it into this R. Now you might be wondering, well, why did I solve for R and not for H? Well, notice that what I'm looking for is for the derivative of H. So that means that in my formula I want to keep my H's. Okay, so here, let me rewrite the formula. If I plug in 3/5 H into here, what I'm going to get is that the volume is equal to 1/3 pi times 3/5 H. If I square all that, I'm going to get 9 over 25 H squared times H. Okay? And so I can simplify this a little bit. If I simplify that, I'm going to get that the volume is equal to 3 over 25 pi H cubed. And now that I have it like this, now I can get the derivative of both sides with respect to time. And this is easier than it was before because I don't have to use the product rule anymore. I only have one variable. Okay, so then what I get is that the derivative of the volume with respect to time, which is what this is equal to, notice that 3 over 25 times pi, those are just constants, so I just leave them out of the whole thing. And then I'm going to multiply that times the derivative of H cubed. Well, the derivative of H cubed, well, that's just 3H squared, and then times, using the chain rule, times the derivative of H with respect to time. And that's, remember, because H is a function of time. As time passes, the water level, this little h, is going to be changing. Okay, and then I take a look. Well, I know that dV over dt is equal to negative. I have that. That's negative 10. So I can plug that in. 3 over 25 pi, those are just constants. Now H, I don't have H. So, but dH over dt is the one that I'm looking for. So to be able to find dH over dt, I need to first find H. And so what that means is that you have to do some more work, use something that you already know to figure out what H is. Okay, so we can't use this formula because we also don't know the radius. Well, what else do we know? What haven't we used? We use the 10, we use the 6. Aha! This guy, we haven't used it at all, right? The volume is equal to 200. Okay. Well, if I know the volume is equal to 200, well, I should be able to use this formula that I found for the volume involving just h, 3 over 25 pi h cubed, and I can use this to find h, because I know that the volume is equal to 200, and then if I solve for h here, I should be able to go back and plug it in. Okay, so let's do that. So then we have, what I want to do is, so let me write this down over here. We have 200 equals 3 pi over 25 h cubed. And so I'm going to multiply both sides by the reciprocal, 25 over 3 pi. 25 over 3 pi, which is going to be, so over here I'm going to have 5,000 over 3 pi. And then over here on the right side, well, these are going to cancel. And this is equal to h cubed. So then I can get the cube root of both sides. So I get that h is equal to the cube root of 5,000 over 3 pi. And this, then I can plug it into here. Now, well, this cube root of 5,000 over 3 pi, well, that's kind of a messed up number. Why don't we approximate that with our calculator? 8.09. Let's round it up to 8.1. 8.1. Okay. So then what we can do is we can use this 8.1 and plug it into this formula for h. So what we would get with this guy is now negative 10 equals, these threes combine into 9 pi over 25 times 8.1 squared times dH over dt. And if we do all this, what we're going to get is that dH over dt is equal to negative 0.13. And this is going to be centimeters per second. And that's it.